This is a presentation of the Mozart programming system by Parley Elecron, Hunter Spakes, and Jeremy Ward. The handout associated with this video is found in the link below. The history of the Mozart programming system: it was designed by Gert Smolka and his students in 1991. His development continued in 1996, the Swedish Institute of Computer Science. Since 1999, OZ has been continually developed by the Mozart Consortium, which originally consisted of Saarland University, Swedish Institute of Computer Science, and Université Catholique de Louvain. In 2005, it is now maintained by the Mozart Board. The Mozart Board is made up of senior community members, and development is now managed by the PLDC Research Group at UCL. So what is Mozart? Mozart is an implementation of the OZ language. We will be using OZ 3 in our examples. OZ is a multi-paradigm programming language developed by the programming systems by the Université Catholique de Louvain for programming language education. What it means by multi-paradigm programming language: this is a programming language that supports more than one programming paradigm. A programming paradigm is just a way of building the structure and elements of computer programs. These paradigms include logic, functional, imperative, object-oriented, constraint, distributed, and concurrent programming. OZ is a high-level language that is designed for modern, advanced, concurrent, intelligent, networked, soft, real-time, parallel, interactive, and proactive applications. A high-level programming language: this just means it uses natural language and can automate significant areas of computing systems, such as memory management, for example. Some of the features of OZ: it allows for object-oriented programming. Object-oriented is a paradigm that represents the concepts of objects that have attributes that describe the object and associated procedures. This provides a compositional syntax, first-class procedures, and lexical scoping. Logic programming, constraint programming, providing logic variable, disjunctive constructs, and programmable search strategies. This is used in other major languages like Prolog, ASP, and Datalog, to name a few. Concurrent language: create dynamic threads. What this means is the threads are dynamic as opposed to sequential. The data flow threads in the sense that a thread executing an operation will suspend until all operands needed have a well-defined value. Executing statements in OZ proceeds only when all real data flow dependencies on the variables involved are resolved. OZ supports network transparent distribution of OZ computations. This is interesting. It means multiple OZ sites can connect together and automatically behave like a single OZ computation, sharing variables, objects, classes, procedures. Then the sites disconnect automatically when references between entities on different sites cease to exist. Language security: all language entities are created and passed explicitly. This means an application cannot forge references nor access references that have not been explicitly given to it. The underlying representation of the language entities is inaccessible to the programmer. Moving on to the OZ data types. OZ is dynamically typed language. Any variable, if it gets a value, will be bound to a value of one of the types shown on the next slide. When a variable is introduced, its type as well as its value are unknown. Only when the variable is bound to an OZ value does the type become determined. These are the OZ data types. As said, it is a dynamically typed language. When a data type is introduced, its value is unknown until it's identified as an OZ data type. Some important examples under value are the chunk, which allows users to introduce abstract data types. It gives us objects, classes, and arrays. The cell, which can modify the state of logic. This space allows problem solving using search techniques. The record, which gives us tuples, literals, atoms, names, which we will see in a moment. Numbers, which gives us floats, integers, and characters, which we will also see in a moment. So here are some of the basic data structures. Numbers, records, tuples, lists. Tuples, a tuple is a type of record, as seen on the previous slide. A tuple consists of a label and values. It's just a record that only has integer features in ascending order, but these features can be omitted. Numbers. OZ supports binary, octal, decimal, and hexadecimal notation for integers. Floats are different. They must have decimal points. There's no automatic type conversion, like 5.0 is equal to 5 in OZ. This will raise an exception. Here is some examples of this. Records, these are structured compound entities. A record has a label and a fixed number of components or arguments. There are records with a variable number of arguments, and these are called open records. And here you can see the label, feature, variable, and then the value that follows. Literals. These types whose members have no internal structure, and they're divided into two types, atoms and names. The atom, a symbolic entity that has an identity made up of a sequence of alphanumeric numbers starting with lowercase. Atoms are empty records, meaning it only consists of a label and has no features. These are created by adding single quotes. A name called by the procedure new name X. Names are similar to atoms, but are a different variable type. The Boolean values true and false are both names of the bool subtype. We'll also discuss lists. A list is a sequence of values ending with nil, much like any other language, and lists are just tuples, which are records, as seen in the previous slides. Some of the strengths of OZ, concurrency. This gives us lightweight, ultra lightweight threads and data flow. Inferency, which allows for constraint and logic programming. Inferency, this is when the data type of an expression is automatically deduced. Distribution, network transparent, open default tolerance, which we have mentioned previously. And flexibility, which makes OZ very dynamic. There's no limits. The flexibility is also a weakness because the execution of OZ is slower than other languages. For example, it was benchmarked at about 50 times slower than that of the GCC compiler for C. Now we will look at the implementation. So let's go step by step through this example of the OZ kernel language. In this example, each possible statement is defined. They are reduced sequentially inside a thread, and values are introduced explicitly and can be equated to variables. All variables are logic variables declared in an explicit scope defined by the local statement here. Procedures are defined at runtime with the proc or procedure statement. State is created by new cell, which obviously creates a new cell. This is an updatable pointer into the variable store. Cells are read by the @ symbol and updated by := or by exchange. Conditionals use if and block until the condition variable b is true or false in the variable store. Threads are created explicitly with the thread statement, and exception handling uses try and raise. Now let's look at some programming examples. This is an example of the hello world. We'll feed the line into the buffer. It is compiled, and it is output as hello world. You can see the name, the atom hello world, the namer command show outputs the atom to the terminal. Now let's look at some other examples in more detail. A thread executing this statement, local xyz in s end, will introduce 3 single assignment variables x, y, and z, and execute the statement s in the scope of these variables. The variables in OZ normally start with uppercase letters, as seen here, and these are possibly followed by an arbitrary number of characters that are either letters or numbers. Before the execution of s, the variables declared will not have any associated values, and we say that the variables are unbound because of this. Any variable in OZ must be introduced except for certain pattern matching constructs that I will show you in a little bit. Another form is a declaration. This is an open-ended declaration that makes x, y, and z visible globally in S, as well as in all statements that follow S textually, unless another variable declaration overrides them. So let's look at the classic hello world example. The program modules in OZ are referred to as functors. The hello world functor, this also requires 2 standard OZ modules, application, which provides executable application termination, and system to provide terminal output. The body functor uses system show as the procedure to print the argument hello world to the screen. So to run that, and as you can see, our standard output is hello world. Here we can use a for loop to display a consecutive list of numbers. We have for a variable x in the list 1 through 10, do this procedure, which is our output, the value of x. And as you can see, we have a list of characters, or a list of numbers, 1 through 10, as our output. OZ also provides a simple form of conditional statement. For example, if B, then S1, else S2, etc., where B should be a Boolean value. If B is bound to true, then S1 is executed. If B is bound to false, then S2 is executed. OZ also provides a simple form of conditional statement. For example, if B, then S1, else S2, etc., until the end. Or B should be a Boolean value. If B is bound to true, then S1 is executed. If B is bound to false, then S2 is executed. If B is not a Boolean value, an exception is raised. Otherwise, if B is unbound, the thread suspends until one of the previous cases applies. So let's look at a program using this. Before executing this example, let's talk about the comparison procedures in OZ. There are several built-in tertiary procedures used for comparison. These include the equals, not equals, equal to or less than, greater than or equal to, greater than. The thing these have in common is they are used as Boolean functions in an infix notation. This example utilizes some of these. This sets the local variables or records, x, y, and z, to values. Z is initially a nil value until it is reached in the loop and assigned a conditional value. So here we have our comparison procedures. If x is greater than or equal to y, then z is equal to x, else z is equal to y. So let's run this program. And as you can see, z is equal to 10. So let's look at it and make sure. X is equal to 5, y is equal to 10. If x is greater than or equal to y, which it is not, then z is equal to x, else z is equal to y, which is 10. So we've seen how to apply a call to a procedure. Now let's see an example of a procedure definition. In the previous example, we demonstrated how to compute the maximum of two numbers or literals using conditional statements, less than, greater than. We abstract the code into a procedure like this. We have our local variables, local max, x, y, z, in a procedure, max, x, y, z. And then we have our if, then else statements. If x is greater than or equal to y, then z is equal to x, else z is equal to y. Just like before, we have the same variable values as before, and then a final declaration and our output. And as you can see, our output is once again 10. Now let's look at a more complex example using these comparisons to create a binary search tree. We still use elements from previous examples, such as our procedure, our variables. One of the interesting things about the procedure variables is the question mark used in front of tree out. This denotes that tree out is the designated output variable in this procedure. In the local variable introduction statement, an implicit pattern matching is performed to extract values of the locally introduced variables k1, v1, t1, and t2. Since these variables have no current values, the output should be empty. And indeed, it is. OZ provides an explicit pattern matching case statement which allows implicit introduction of variables in the patterns. Case statements can also be used such that case E of pattern 1, then S1. Pattern 2, then S2. And so on, else S. Now we will see an example of a binary tree using case statements. Here we have the same tree, except we use explicit pattern matching using the case statements as opposed to the implicit pattern matching from the previous tree. In this, the procedure variables are the same, the local variables are the same, and the tree runs the same explicitly as opposed to implicitly. Again, with no values to the variables, our output is empty. The stable versions that have been previously released are version 1.3.2 and 1.4.0. The alpha of Mozart 2 has been released, but was not usable in these examples. Thank you for your time and attention.